In previous courses, we've learned that 5G will change the way of live broadcast, allowing us to shoot and transmit videos simultaneously. What changes will 5G bring to power grids with its high bandwidth, low latency, and massive connectivity capabilities? This is the topic of this course. First, let's get to know the power grid. A power grid consists of 5 parts: power generation, transmission, transformation, distribution, and consumption. Common generation modes include thermal power, hydropower, wind power, and solar power. Common transmission modes include UHV, EHV, and HV. Common transformation modes are step-up transformation and step-down transformation. Common distribution modes include high voltage, medium voltage, and low voltage power distribution. Common consumption modes include residential, commercial, industrial, and agricultural power consumption. To ensure the smooth operation of power grids, power companies usually construct a communication network to monitor and control the power grid devices. For generation, transmission, and transformation, power companies usually use self-built private networks. Optical fibers are directly connected to sites to provide highly stable communications. However, for distribution and consumption, few optical fibers are deployed at sites due to widespreading of power distribution lines and massive amounts of user equipment. This is where operators' mobile communication networks come in. In the future, these networks can be used to implement intelligent services for the last-mile power distribution and consumption. On traditional power grids, mobile communication networks have already been used for power distribution and consumption, but there are many problems. For example, the GPRS network has low online rate but high latency and is not suitable for remote control, sensing, and measurement of power grids, nor can it support large-scale access of electric appliances. In addition, HD video surveillance on operators' 4G networks is affected by low bandwidth and high costs. Therefore, future smart grids must rely on 5G networks with high bandwidth, low latency, and a massive connectivity to perform intelligent reconstruction of the last-mile grid services. With a rapidly maturing new energy, new devices, advanced sensing technologies, and information technologies, traditional grids are gradually evolving to smart grids to achieve clean and environment-friendly generation, safe and efficient transmission and transformation, flexible and reliable distribution, and diversified and interactive consumption. In the future, with explosive growth of data collection requirements, energy systems will be deeply integrated with Internet technologies, and smart grids will further evolve into the energy Internet. The final goal is safe, reliable, green, and efficient smart energy. During this process, current communication networks still face many challenges, including: first, differentiated service adaptation. The various grid services have diversified requirements on communications bandwidth, security, latency, and cost. Second, data transmission security. If grid control services are maliciously attacked, serious power failures will occur, severely impacting social stability. Third, low latency and high reliability. Grid control services such as power distribution automation and precise load control require ultra-low latency and ultra-high reliability to ensure that communications channels are measurable and controllable. Fourth, large-scale and low-cost access for terminals. Currently, there are millions of grid communications terminals. In the future, the number may reach tens or even hundreds of millions. A system providing low-cost network access is needed to replace high-cost private networks currently in use. Faced with these challenges, communications requirements of future smart grids include diversified services, network security, and high performance. Considering the high construction costs, future smart grids must also be more cost-efficient. How do we meet these requirements? 5G network slicing is the answer. On-demand deployment of 5G network slices allows for customized network functions and architecture for each service. Resource isolation can construct a logically isolated private network on the shared telecom infrastructure to ensure security. Service level agreement enables ultra-low latency and ultra-large connections of power grids using 5G and MAC, implementing ETE SLA assurance. Automatic O&M implements automatic deployment and operation on the shared infrastructure, reducing costs. Next, let's look at some typical application scenarios of smart grids. First, millisecond-level precise load control. When a fault occurs, the stability control system as the second line of defense cuts off the load to ensure grid stability. Low-frequency and low-voltage shedding devices as the third line of defense shed the load to prevent grid breakdown. The current control mode is coarse-grained. Once a fault occurs, the entire power distribution line is cut off, causing large-scale power failures. Therefore, a fine-grained control mode is in need to extend terminal control points, so as to preferentially cut off interruptible loads such as cooling instead of cutting off the entire line. In this scenario, ultra-low latency, ultra-high reliability, and service isolation are the main requirements. Second, low-voltage power consumption data collection. Low-voltage power consumption data collection is a system that collects, processes, and monitors in real time the power consumption data of users. It automatically collects power consumption data, monitors meeting exceptions and power quality, analyzes and manages power consumption, releases related information, monitors DER, and provides information exchange among smart power-consuming equipment. Currently, the data collection is small in scale and low in frequency. The collected data is mainly used for metering. In the future, the collection scale and frequency will increase, and the collected data will be used to guide off-peak power consumption. In this scenario, a large number of terminals need to frequently and concurrently access the network. The third scenario is drone grid inspection. Drones can remotely inspect power lines, wind power plants, and PV power plants. With a low latency and high bandwidth of 5G networks, drones can shoot videos and simultaneously send them back, while the background system uses AI algorithm to identify problems and provide suggestions. In early days, power grid inspection is performed manually using cameras and telescopes. Combined with manual analysis using handheld instruments, the efficiency is low. With 5G, drones will be used for NLOS inspection, shooting while transmitting, and remote AI algorithm can detect problems in real time, greatly improving inspection efficiency. Drone inspection requires ultra-low latency, high bandwidth, and ultra-high reliability. The 5G smart grid solution consists of 3 layers: terminal layer, network layer, and application layer. The terminal layer is responsible for collecting grid data and executing control commands. The network layer provides communications channels to ensure high bandwidth, low latency, and large-scale network connections. The application layer provides various types of grid applications to implement smart grid evolution. How will different smart grid applications be implemented in the future? This is where 5G network slicing comes in. The smart grid is sliced into radio access network slice, transport network slice, and core network slice. Different grid applications have different network requirements and thus different slice architectures. To this end, 5G network slices need to be customized for different services. Take low-voltage power consumption data collection and precise load control as examples. Low-voltage power consumption data collection is insensitive to latency and requires large-scale terminal access. Therefore, when designing this slice, the control plane and the user plane NEs of the core network are centrally deployed in the core data center, but gateways are not moved to regions. However, on the RAN side, to ensure the access of a large number of terminals, low-frequency signal coverage is required. Precise load control is sensitive to latency during slicing design. To reduce latency, core network gateways and related servers are deployed in edge data centers based on MEC solution. This shortens the distance between load control terminals and related services to achieve millisecond-level low-latency control. While latency-insensitive NEs can still be deployed in the central data center, How to ensure security of different slice services in the future? Hard isolation of 5G network slices will solve this problem. On the RAN, different slices can use different time frequency resources to send signals so that signals are isolated in the air. On the transport network, different slices can use the FlexE technology to implement hardware isolation of transmission resources. On the core network, different network function entities and microservices can be customized for different slices to implement NE level or service level isolation. Hard isolation of 5G network slices and the IPsec tunnel technology can ensure end-to-end data transmission security. Currently, 5G smart grids have been deployed in multiple scenarios. For example, a power grid company in China has been using drones to inspect power grids, including high-voltage power lines, wind power plants, and photovoltaic power plants. However, the inspection area is yet to be covered by 5G signals at present. Therefore, drones are used for LOS inspection. Drones are remotely controlled to collect data, which is manually imported to the analysis platform for fault diagnosis and suggestion output. The power grid company expects that in the next 5 years, drone inspection covers more than 90% of the 110 kV and 220 kV lines, covering almost 600,000 kilometers of power lines. Drones would take up more than 70% of the inspection tasks. For millisecond-level precise load control, a power grid company in Nanjing, a communications company in Nanjing, and Huawei conducted joint tests. The tests focused on verifying the E2E latency of precise load control for eMBP services based on 3GPP Release 15. In the test, the 3400 to 3500 MHz 5G band, the 100 MHz bandwidth, and a Huawei 5G CPE are used. 5G base stations and 5G core network are based on the IP RAN. The 5G core network uses the E2E network slicing technology. 100 megabit per second optical fibers link up the core network equipment room and the power company's main site for precise load control. In this test, the average E2E latency is 37 milliseconds. The latency from the 5G core network to the CPE is 4.5 milliseconds. The latency from the 5G core network to the precise load control subsite is 0.5 millisecond, and the rest latency occurs in the control command delivery by the subsite and command processing by the load control terminal. The test result verifies that the low latency feature of 5G can meet the requirements of large-scale deployment of precise load control services in the future. In this course, we have learned about 5G smart grids, the development status of power grids, and the requirements of future power grids. The E2E 5G network slicing technology can meet differentiated service requirements of 5G smart grids. We've also seen some use cases of 5G smart grid solution. That's all for this course. Thank you for watching.